Hi everyone, I am Shomo, a final year graduate student at Vanderbilt University. Today I am going to present our paper called Collaborative Navigation Improve Spatial Learning Across Symmetric and Asymmetric Locomotion in Virtual Reality. Because of the technological advancement in VR, multiple people can join in a shared virtual environment from any part of the globe. If they perform collaborative navigation in the shared virtual environment, they can choose either symmetric locomotion methods like all of them can use steering, or they can choose asymmetric locomotion methods like they can use a combination of steering and teleportation. However, most VR applications do not support asymmetric locomotion methods for collaborative navigators, probably because of easier development, and developers probably assume that one locomotion method fits all. Past research shows that individuals often prefer different locomotion methods based on their effect on cybersickness and spatial knowledge acquisition. Also, people with physical disabilities might need special devices or special locomotion methods to interact with and navigate through virtual environments. So, allowing asymmetric locomotion methods can let users navigate using their preferred locomotion methods, which can reduce their cybersickness and boost productivity. Now, even if we assume that future VR applications will allow asymmetric locomotion methods for collaborative navigation, we still don't know how it affects spatial acquisition and cybersickness of the collaborative navigators. So, in our study, we investigated how well dyads acquire survey knowledge in shared virtual environments using asymmetric locomotion methods compared to symmetric locomotion methods. To answer our research question, we chose two very popular virtual locomotion methods, that is steering and teleportation, and we asked several groups of two people or dyads to use these locomotion methods while navigating collaboratively. We call this group as asymmetric navigation group. To compare their performance, we recruited two separate baseline groups of dyads. One was the symmetric steering group, where both partners used steering, and the other was the symmetric teleportation group, where both used teleportation. Within each group, participants had to perform an individual navigation phase where each person navigated through the virtual environment alone with the assigned locomotion method. And they also performed a collaborative navigation phase where the dyad navigated the environment together with their assigned locomotion methods. In each navigation phase, there were two phases in the experiment, that is, the learning phase and the testing phase. The learning phases consisted of two different virtual mazes of 10 meters of side length on each side, where the participant explored for 10 minutes to form cognitive maps. The testing phases consisted of the ground and the skybox from the mazes only. Participant survey knowledge of the mazes was tested in this environment. Here is an example of a participant exploring the maze environment during the learning phase using the teleportation technique. Her position is represented in the maze environment from a bird's eye view for understanding the locomotion method better. During the trials, the participants were placed in front of an object in the maze. Once they pressed a button on their dominant hand controller, the entire maze environment vanished. Their task was then to travel in a straight line using their locomotion method to find the estimated location of another object. Similarly, during collaborative navigation, dyads learned the environment collaboratively using their locomotion methods. They were physically distributed, but they could see and hear each other virtually. Finally, in the same way mentioned before, they were asked to test their acquired survey knowledge during the testing phase using their locomotion methods. We recruited 96 participants for the study, including 56 females and 40 males ranging from 18 to 43 years old. The independent variables were dyad locomotion method groups, that is symmetric steering, symmetric teleportation and asymmetric navigation groups, locomotion methods, that is steering and teleportation, navigation phases, that is individual and collaborative navigation phases, and phase order, that is whether the dyads experienced individual navigation first or collaborative navigation first. The dependent variables were absolute angular error, proportional distance error, recall time, and VRSQ scores to measure cybersickness. Our first hypothesis was dyads will outperform individual navigators in the navigation task, regardless of locomotion method. To test this hypothesis, we used multi-level models on mean angular error, distance error, and recall time across trials. We found a significant main effect of navigation phases on angular errors. Dyads had significantly lower angular errors during collaborative navigation than when they navigated individually. However, this main effect was qualified by a significant interaction between navigation phase and phase order on angular errors. Dyads' angular errors decreased significantly only when they experienced individual navigation fast. However, there was no significant difference between their individual and collaborative angular errors if they experienced collaborative navigation fast. Also, for this group, the overall angular errors were extremely low, meaning they estimated directions very accurately. We found a similar pattern for distance errors also. That is, distance errors of dyads decreased significantly only when they experienced individual navigation fast. But there was no significant difference between their individual and collaborative distance errors when they experienced collaborative navigation fast. Also, this group was very accurate in distance judgments. Overall, these findings indicate that initial collaboration has positively influenced individuals' directional and distance accuracy so that they perform better later. And dyads outperformed individuals in estimating directions and distances across all locomotion methods, which supports our hypothesis 1. Regarding recall times, we found that dyads took longer than individuals to recall, suggesting that they took more time to fine-tune their judgments, which resulted in better accuracy. Our second hypothesis was individuals using steering will achieve better results than those using teleportation. To test this hypothesis, we ran a 2x2 between group ANOVA on mean angular errors and distance errors across trials during the individual navigation phase only. We found that individuals who used teleportation had significantly lower angular errors than those who used steering. We did not find any significant main effect of locomotion methods on distance errors among individuals. A possible reason for this could be that steering-related cybersickness could negatively impact individuals' judgments. For both angular and distance errors, we found that individuals who experienced collaborative navigation fast had significantly lower errors than those who experienced individual navigation fast. Overall, this finding suggests that teleportation produced lower angular errors than steering and helped individuals to judge distances as effectively as steering, which does not support our hypothesis 2. Also, we found that initial collaboration has positively influenced individuals' directional and distance accuracy across all locomotion methods. Our last hypothesis consisted of two parts, and they were dyads in the symmetric steering group will excel in the navigation task compared to the other two groups, and dyads in the symmetric teleportation group will perform worse than the other groups. To test this hypothesis, we ran a 2x2 between group ANOVA on mean angular errors and distance errors across trials during the collaborative navigation phase only. We did not find any significant main or interaction effects in the data. This suggests that dyads using asymmetric locomotion methods performed as effectively as those using symmetric locomotion methods, which does not support our hypothesis 3. To analyze cybersickness among the participants, we ran a 3x2 mixed ANOVA on mean VRSQ scores after each navigation phase. We found that symmetric steering group became significantly more cybersick than both the symmetric teleportation and the asymmetric navigation groups, whereas there was no significant difference between the VRSQ scores of the asymmetric navigation group and the symmetric teleportation group. Overall, this finding suggests that asymmetric locomotion methods imposed comparable or less cybersickness than symmetric locomotion methods among dyads. So, the main takeaways from this study are that collaborative navigators acquired better survey knowledge than individual navigators irrespective of locomotion methods. Second, asymmetric locomotion methods did not impair dyadic learning significantly compared to symmetric locomotion methods. Third, contrary to several prior findings, teleportation enabled individuals to acquire survey knowledge as effectively as steering. Fourth, asymmetric locomotion methods impose comparable or less cybersickness than symmetric locomotion methods among dyads. And finally, based on our results, we can suggest developers to support asymmetric locomotion methods in their applications, which might be helpful for the users. Interestingly, we also found that initial collaboration improved later individual accuracy. This was not a practice effect because we deliberately altered the object locations and rotate the measures between tasks. This study does not answer why initial collaboration improved later individual accuracy. Our future study will address this question in depth. Thank you for listening to my talk and enjoy the rest of IEEE 2026.